So, if you look at the structure, you see one thing is effect of temperature on the material, but structural behavior, the material loses its strength, all right, but structural behavior sometime, as you can see, the support conditions when you look at structural element, its deformation properties, right, or load carrying capacity is not only the function of material properties, but it is also function of its support condition, because your bending moment or forces, if I may call it in general, axial forces or bending moment, etc., they would depend upon how the load is transferred to that structures from surrounding elements. So, their end conditions are important. Now, as an example, consider this: if I have no fire, before fire the load deformation would have been something like this, right, and during the fire it might nullify the bending action, because here the expansion would now occur here and it is restrained here. So, if there is an expansion at the bottom and top is expanding less, because temperature differential would be something like this: high temperature here, high temperature here, low temperature here. So, you will have a kind of it will try to expand here, and if you have restraint, then there is a compression in at the bottom, because higher expansion tendency, but you are holding it. So, therefore, you are compressing at the bottom, while top is restrained, but expansion is less. So, net effect is as if you are pushing from both the side, right, at the bottom mode. So, it is like your it is like applying an eccentric load, applying the eccentric load with the eccentricity, or the load is being applied below the neutral axis. So, you apply an axial force below the neutral axis, it will have a tendency to bend. So, it will nullify the effect of flexure which was there earlier. Also, it will induce a kind of push stresses to the supporting structure. It will so structural behavior deformation plus thermal stresses, if you see, net effect has to be seen of this, of both. Now, simple cases earlier people were designing for fire resistance, or understanding of fire resistance is only related to material. For example, I said if you take steel, the moment it reaches 550 degree centigrade, okay, you say the system is it's reached its fire resistance, but that is extremely conservative, because that is not taking account of the end conditions of the element. So, element by element one should do a thorough analysis, or maybe the whole structure. So, structural fire design today, it looks into the structure as a whole, its behavior under the simulated fire. Under simulated fire, could be, I mean, theoretical if it is, then it is simulated fire, or might put standard time temperature curve, its temperature and time is curve is known. So, that condition you take inside the room, and then try to find out how each member would be affected due to this, because both the effect of their properties as well as end condition changes, modulus of elasticity, bending moment, everything you would one can see. In our case we are not looking into this, because structural fire design would be a subject, will be a subject someday, because till date it's still in good lot of research stage. So, that is how it is. One more material I want to, so that is related to structural materials. One more material I would like to introduce to you is gypsum. Gypsum is used often as a protection for steel. Why? You see, what is gypsum chemically? Chemically, gypsum is calcium sulphate 2H2O, right. Calcium sulphate anhydrous calcium sulphate, and then when 2H2O goes, it forms crystalline structure, and that is gypsum. Now, this is this crystalline structure, this goes chemical combination, it is chemically combined water. As I said, crystal formation only occurs when you have appropriate packing density. Now, you see, sulphate is an anion and its size is very large. You know, it's calcium plus 2 calcium and SO4 minus 2 minus, right. So, you have radical SO4 and calcium. They try to arrange themselves in some regular order. When they try to do that, the volume occupied by this is much larger, because SO4 large molecule is large. This does not happen in case of many other, sodium chloride for example. Its crystal by itself does not require water. The molecules are, atoms are of the similar sizes, where the sizes of this is very large compared to this cation. So, they would be occupying like something like this, right. The void space in between is too large for crystal to become stable. So, what it does? It actually takes water from outside wherever it is available, and then puts water also into the system, water molecule also into the system, chemically combined H2O, chemically combined H2O system, and this crystal is stable. So, is copper sulphate 5H2O. And you remember why I brought in copper sulphate is, you would have studied in school chemistry that you can't remove this water very easily, because they are chemically combined, like CHS, calcium silicate hydrates, this H is chemically combined. So, what you do, you can remove some water at lower heat, lower temperature, less heat, and to remove all the water you need lot of heat. So is the case with calcium gypsum. When you want to remove, first you have to remove the water out of it, and this absorbs a lot of heat. So, it can take a lot of heat to become anhydrous calcium sulphate. Gypsum will take a lot of heat. So, if you have fire on this side, let us say 1010 degrees centigrade in flame, or 1850 Fahrenheit, or 450, So, you will find that if you have a thickness, small thickness of gypsum, it itself will get first calcine, it itself will get calcine to a depth of about 2 inch, right, or 50 mm you can say, where the temperature will be 100 degrees centigrade or so, because this solid gypsum has absorbed all the water, all the heat to liberate the H2O out, and then this, so it acts like an heat absorber, heat sink. That is why gypsum is very good. So, you would see many of the buildings you will see gyp boards, gypsum boards. If they are steel, they would be either covered with gypsum, or modern day there are other kind of like polymers I was mentioning. Polymers are, they can be synthesized, and you can design the material, polymer composites. So, for example, polytetrafluoroethylene, PTFE, you use it very often. Teflon, so use Teflon coated frying pan. Now, you see it is also a polymer, and polythene is also a polymer. Now, that withstand 1800, 2200 degrees centigrade, while this one just does not. So, you can have variations. So, there are fire retardant coating, polymeric coating, many of them are patented maybe. So, either those kind of thing or gypsums are used for applied, they are applied on top of the steel in order to protect the steel from fire. So, gypsum is a good fire, fire protection devices. For example, this is what it is: gypsum, this is steel section, and I have a kind of gypsum spray. So, this will ensure that this steel is protected, because steel is vulnerable. And like localized heat generation, and steel is a good conductor. So, localized heat generated would get transmitted easily to other parts as well. While these are these inorganic materials, particulate material like ceramics and such system, that concrete and chemically combined ceramics or otherwise, they are not good conductors, they are insulators. So, as a result, they do not transmit the heat. Now, steel, it starts heating fire at one place, it will easily go to other places as well, So, steel needs protection, and you can see that it withstand much less temperature, 550 degrees centigrade. We say that it collapses. Somewhere there might be a hinge formation, it will warp, plastic state, hinge formation would occur, and if sufficient heat plus thick hinges are formed, the element may collapse also. Normally that's unusual because fire doesn't go to all places till the flashover occurs, and where it is actually locally, all places hinge formation will not occur. One place it has formed, it might form a mechanism or may not form a mechanism, right. So you have to analyze the whole thing. But supposing I have put in gypsum cover, still it's vulnerable. I have put in gypsum cover or something of that kind of thing, it can withstand much longer period of time. Structural stability is better against fire. So gypsum spray or gypsum board, these are the gypsum board used around steel in order to protect steel. You will find gypboard false ceiling all over the place. That's one of the reason is it will not spread fire. They are very good against fire. So steel also can be encased in concrete. I can encase them in concrete. Steel is either exposed steel is rarely used. I will either encase in gypsum board, spray gypsum, or encase them in concrete, because concrete is good insulator. Now thermal conductivity of steel, we shall see it again later on, is 50 watt. Concrete would be 1 to 2 watt. So 25 times more, nearly 25 or 25 times more, 25 or to 50 times more somewhere. Okay, let's say it's 2.5, somewhere around 20 times more. So steel has got high conductivity, concrete has got much less. Gypsum, this is the case I was saying, very useful since it will absorb a lot of heat while losing water, and the remaining calcium sulphate is also good insulator. So gypsum boards, that's why we use it, right. The other kind of thing which were used earlier days were called water column. Water has got highest specific heat, right. It's compared to let us say concrete, it will be about more than 4 times. Concrete to thermal specific heat, because it's around 4.270 something of this order. Order is this joules per kg, right, 4.27 etc. kg per degree centigrade, and concrete would be order of 1000 kg per joules per kg degree centigrade, right. Many of these materials, that concrete brick will be 900, 800 to 1000, 800 to 1000. So specific heat of water is much higher. Okay. Density, of course, so thermal capacity is multiplied by density, so 2400, and this will be 1000 multiplied. So it will go accordingly, but water can absorb heat. But more importantly, water is a fluid, it has got high specific heat, it can also convect, by convection it can transmit the heat. So water columns were used. These columns are interconnected to an overhead tank which has a vent for vapor to escape. So how does it look like? So you have hot liquid sorry you have hot liquid, water, steel here. So the heat, so for example somewhere the flame is 1200, 1000 degrees centigrade, you will have. So this should come down significantly here, because liquid here, the water will get heated up and it will transmit. If all the column, whole of the column is all affected by fire, then there is a different case. But when fire starts, the water in that particular column, so this will be a rectangular column, cross section should be something like this, cross section, it will be a closed column, it has to be a closed column filled with water. So when heat comes in this surface, it will get heated up, the water will go out, and it's connected to other columns as well by circulation, convection, the fresh cool water will come in, that will take the heat. So heat gets transmitted from here, and this is how it actually maintains. So water filled columns are used, something like this should be there. You have a tank on top, all the columns are connected through this pipe system, all the columns are connected through this pipe system, right. So this all columns are connected here, all columns are connected here, right, they are connected, and there is a bottom connection also, and there is a connection here also. So all the columns are connected, top and bottom, right, top and bottom. So, there is a tank up. So, what will happen if you have fire here, the water will move upward and cool air from the water from other places will come. That is how it will remove the heat, and hot water will have a tendency to accumulate here. There is a vent here, the vapor would actually go out. This was used, but it is not a very, it is fairly cumbersome. You have to also see that you protect the steel from corrosion process. Metal, moisture and water, aqueous corrosion can occur. So, painting, and of course, the lack of oxygen availability has to be there. Partially wet scenario where corrosion occurs much faster. So, that's related to some of the material related properties, some of the material related properties we can look into. Now, based on these concepts, design for fire resistance. We can look from this, based on this concepts, we can consider, we can design for fire resistance. We can design for fire resistance. All right. So, designing for fire resistance is what we will look into. Simple cases. Actually, today, if you want to look at a full structure, simulate the fire, and as I said, softwares can do that, like Abacus does, or like fire simulation will be done by CFD models and all. But in the class, we are looking at simple cases of fire design for steel, which is simple, so that you understand the principle that would be there. But that is design of an element irrespective of its end condition, support condition or structural behavior. That is what we will do in the class. That is very conservative. In actual structure, the end conditions and behavior of the whole beam or column must be looked into. We are not looking into that. All criteria that we are using is that 550 degrees this is the criteria we are using for fire resistance. So, as soon as the steel reaches 550 degrees centigrade, we say that that is the time of its fire resistance. So, that is only a thermal design. Really the structural part we are not looking into, we have simplified it actually. So, that is very conservative, So, reinforced concrete, what is the criteria? Temperature of the rebar should reach only 550 degrees centigrade, because concrete is not as vulnerable, it is an insulator, it protects the reinforcement bar. But reinforcement bar is what provides tensile capacity to concrete. So, if the reinforcement bar is not effective in carrying the load, the cracks would develop in concrete and it will eventually collapse. That is again the concept. So, this is also fairly conservative way of looking at it, right. Now, as I said, conductivity of concrete is very low, of the order of 1 to 2 watt-meter degree centigrade. And if you look at Indian Standard Code IS 456, more fire resistance means you want higher fire resistance, you require more cover. So, it gives you a table where cover depth for fire resistance against fire resistance is given. So, if you want 1 hour fire resistance, cover depth required is relatively less, 2 hours more, and so on and so forth. So, cover depth now in 2000 code or now modern all codes is governed by not only by your durability prescription, attack from aggressive environment, but it also depends on fire. So, sometimes you will find for fire resistance you require higher cover. So, that is what they have done, right. But you cannot go on infinitely increasing the cover depth, although concrete is cheaper than steel, because then you got to restrain, you will have to restrict the strain level at the steel, otherwise concrete will crack. You have a section like this is your RCC section. If you have steel somewhere there, steel shear, right. Effective depth is something D, you call it effective depth, the steel is somewhere here. Now, supposing I increase the cover depth, now at this level, you remember the strain is fixed at 0.002 plus 0.87 Fy divided by E of the steel. That is what it is, you remember that is what we do, right. So, that is the strain. Now, if this is the strain diagram will be something like this. Strain diagram will be, this is a neutral axis is somewhere there. Strain diagram will be something like this. So, if I maintain this strength, if the cover depth is more, the strain will be more at the bottom of the concrete face. Cracks will appear, because tensile strain capacity of concrete is generally low. So, if I increase go on, make it something like this, the strain is very high onto the cover concrete, so it will crack. So, that is not, it is not, so increasing, you cannot go on increasing the cover just like that. So, but cannot increase infinitely, more the cover, more the strain of the steel, also extra material, right. Otherwise, you will not be and if you do not increase the strain in the you say that bottom fiber of the concrete will be restrict the strain there, the steel may not yield at failure, at ultimate load, and therefore, it might be a brittle failure. So, the consequences are that way. So, you just cannot go on increasing, right. So, that is the idea, but then minimal cover is specified for given fire resistance. So, we will look into design of simple steel section for fire resistance. Let us say L is the thickness of the material, this is the temperature according to standard fire, Ta plus 345 log 8T plus 1, that is what formula I have given you earlier. So, we assume that steel section is engulfed in fire fully, right, steel section is engulfed in fire fully. Okay. So, if that is the case, heat transfer to the steel will occur how? Okay, let us have a, let me draw this for you. If this is my fire, this is the all side, both sides, all sides I am saying fire is there, and my steel section is something like this, let us say a rectangular steel section. Simple case I am taking, let us say it is a fabricated engineered structure made from plates, just simple, although real system will be either I or 2 channels. It could be 2 channels in fact. It is engulfed by fire from all direction, right. Now, how will the heat be transferred? Heat transfer will occur, from this to this steel. What mode? Radiation, because this is all flame. So, flame is hot, from hot flame by radiation, plus hot gases are here by convection. So, steel if it is cold, hot gases will come in contact with the steel, pass on the heat, and more hot gas will try to tend to, I mean they will try to, it will try to move, cold gases will tend to move downward, hot gases will move from. So, radiation plus convection, and we assume the steel is a very good conductor, therefore, steel temperature is uniform in all these places. Since it is flame is a gas phase phenomena, it is a fluid phase phenomena, only radiation and convection will be, mode will be the heat will be transferred to the steel section by radiation and convection mode. All right. So, you look at that heat transfer. So, you remember we talked in terms of radiation heat transfer was Q, red. We said that it is governed by Stephens-Boltzmann law, which will be sigma epsilon area multiplied by T gas to the power 4 minus T steel to the power 4. That is the formula. Radiation heat transfer is this formula, right. Now, here area will be steel surface which is engulfed in flame from all direction. Sigma is the Stephens-Boltzmann constant, Tg is the fire temperature, and Ts is the. So, this is how per unit time, watt would this much watt or joules per second it will go. Now, what we do is we assume a small time step of delta T. During this period of time, the heat that would be transferred will be this multiplied by, this is per unit multiplied by delta T, right, and this will go on raising the temperature of the steel from Ts to Ts plus some delta temperature, which I call as T, S T S I plus 1. So, T S I plus 1. So, I can assume small delta T time step during which heat would be transferred from the flame to the steel section, and it will go on storing that heat, or its temperature will be raised. So, initial temperature, next step temperature, in this manner I can go on calculating. Now, I have only taken radiation. Convection heat transfer is relatively simpler. The Q convection is H convective heat transfer coefficient multiplied by same area multiplied by T g minus T s. This is ith temperature, this is ith time step, ith time step, because it is linearly related. So, so this is how we can find out. So, this formula is here now for you, this formula. So, heat transfer, this is the radiation part, because this is in absolute, it is in Kelvin. So, T g I plus 1th time 273 to the ith time into delta T, because this is the rate of heat transfer per unit time, area of the steel, epsilon is emissivity, what we call equivalent, it's basically given by 1 by epsilon is given by 1 by epsilon of the flame plus 1 by epsilon of the steel minus 1, I think minus 1, that is how it is. One calculates this out, effective emissivity for the two exchange surfaces using this kind of a formula. Anyway, we are not going to calculate from basics, but this is known to us. This is convective part, this is also known to us, this is the area of the steel, and that is how I can find out. Now, this causes an increase in the heat content of the steel. So, Cs is the specific heat of steel, V is the volume of the steel. If I take 1 meter height or 1 meter length of the steel, density is rho s, this is the temperature difference, this is the amount of heat stored. So, heat coming in a time step during delta T time is this much, this must go on increasing the temperature. It is basically a explicit finite difference formulation, explicit finite difference formulation. Everything else is known to you, because this will be known to you from the formula. This is the previous time temperature of the steel, right. These properties are known to you, area of the steel is known to you, this density of steel is known to you, we will do one calculation actually, volume of the steel we know, specific heat of steel is known, and this is the unknown temperature at the next, after this time step, this is known. So, we can find out, explicitly find out T s I when we equate these two, because Q stored must be equals to Q coming in, right. So, Q in must be equals to, by equating heat input into the heat stored, we can work out the time required for the temperature to delta T to go to 550 degrees centigrade. So, by equating this heat coming in to the heat stored, I can find out temperature change in every time step. Go on repeating this till the temperature of the steel becomes 550 degrees centigrade. Total sum of the total time step, that gives you the fire resistance, right. So, we do it in a tabular form. For example, consider this section, box section, let us say I have got 200 mm and 200 mm with thickness of 15 mm engulfed in fire from all sides, right. So, this is my steel section engulfed in fire from all sides. So, I have got fire from all sides, fire. This is a vertical section, let us say it is a column, let us say it is a column. I consider 1 meter height. So, it is column, fire on this side, all sides, fire, right. This properties, equivalent emissivity of flame and steel is generally taken to be 0.65, and Stefan Boltzmann constant is 5.71 into 10 to the power minus 8. Density of steel is 7850 and convective heat transfer is 0.023 kilowatt per square meter Kelvin. Specific heat of steel is 0.54 kilojoules per kg. So, these properties are known. I can set this equation. Time step, let us say I am taking a larger time step, you can take smaller, but it makes not much of a difference. Take 1/22 time step delta T is equals to 120 and ambient temperature is 25. I first find out a constant which covers the radiation heat transfer divided by rho s Vcs. You know, if I equate these two equations earlier that I was showing, earlier equations, these two equations if I equate, then I will get this part will be obtained by simply dividing this by rho s Vcs. You know, this will be divided by rho s Vcs. So, Ts1 I want to find out explicitly, I will be simply doing this, dividing by this and then add Tsi at the next step. So, that is what we do in tabular form. Tabular form exactly we do the same, right, 7850. So, this is given and this is what I find as A divided by rho s Vs, you know, this part the radiation heat transfer component Vc, this will be multiplied by delta T, that is 120, and this is the convective heat transfer part divided by rho s Vcs. After first time step temperature is 64, one can calculate this out for this particular case and is 109. After 8 steps temperature becomes 550 degree, 55 degree centigrade. Thus, fire resistance is 120 into 8 seconds, right. So, that means 8 into 2 16 minutes, 16 minutes that is what it is. Okay, this is done in tabular form. You can you know I'll since I'll be uploading this, you can find it out. To start with, Tg is 25 plus 273 in Kelvin 298, right, to start at time step 0. Time step, this is delta T is equals to 120 and we will calculate some of this in the next class, and we can make this kind of table and you can see that this temperature goes to 555 after 8 minutes. Therefore, fire resistance is 8 time step, 2 minutes, 4 minutes, 6 minutes, 8 minutes, 16 minutes, that is all. Okay, we will stop at this point.